Hey guys, this is the start of Chapter 4. We're going to cover Section 1 today, and it's the development of the new atomic model. If you think back so far, we've already talked about Dalton's model, Thomson's model, Rutherford's model, and now we're going to learn of a new model today. We've got a couple definitions that you need to get down. Electromagnetic radiation. It is a form of energy that exhibits wave-like behavior as it travels through space. You get to see electromagnetic radiation all the time as far as the light that you see and the colors that you see. We're going to talk a lot about that today. And when you put all of those forms of radiation together, you have the electromagnetic spectrum. And we're going to go look at all of the main parts of the electromagnetic spectrum. We're going to draw it out. We're going to label them. We're looking at 7 main types for us today, and we're going to look and see how wavelength and frequency are related to this. We will come back to this drawing. We're going to do our own drawing, so don't draw just yet, but we will look at the electromagnetic spectrum. I'm going to get you 2 more definitions, and that is for wavelength, which is the distance between corresponding points on adjacent waves. So think of a length. And then we have wavelength. And frequency, it's the number of waves that pass a point in a specific time, usually 1 second. The 2 symbols that you're going to see me draw are, we've got this one right here, which is lambda. It almost looks like an upside down Y. So when I draw it, mine usually look like that. And the other one it looks like a V or a cursive V. That is nu, N-U. Both of these are Greek symbols that we're working with, and that's how we'll draw what looks like a V. So wavelength and frequency. You can title this the Electromagnetic Spectrum, and we are going to look at 7 types of electromagnetic radiation that make up this full spectrum, and we'll break it down a little bit too. So starting off here at the bottom, we're going to have 2 lines representing. One is going to be representing wavelength, and the other is going to be representing frequency. So we've got wavelength and frequency that we're going to represent. Hopefully you have your colors out too. This is a great opportunity to get those colors going. And I'm just trying to make it to where later on it's going to be easier for you to look at. And if you look in the book, whenever you get back to class, you will notice this drawing in your book too. So for wavelength, we've got the ends of this are 10 to the negative 2 nanometers, and the opposite end is 10 to the 4th meters. Nano, if you think of nanotechnology meaning very, very small, that is an extremely small wavelength to your left, and then 10 to the 4th meters, that's like 10,000 meters. That's an extremely long wavelength that is to the right. On your frequency, we have on one extreme 10 to the 19th hertz. Hertz, Hz, I'll write it up here real quick so that you can write it down. That is our unit that we are using for frequency. It's called the hertz, abbreviated Hz. And on the other end of that, we have 10 to the 5th hertz. So you should know that 10 to the 19th is a much larger number than 10 to the 5th. That's what we have here as far as our extreme outsides for hertz. Hopefully you notice that the really tiny numbers for wavelength, we have really small numbers here, but very large numbers on this end. And for frequency, we have very large numbers on this end, but really small numbers on that end. So I'm kind of drawing little dots so that you can see they actually move in the opposite direction. We are going to draw a piece out of this. I'm going to draw it right around here, because when we label our radiation, we are going to talk about visible light. So it'll go there. So next is going to be the 7 types of electromagnetic radiation. We're starting first with gamma rays. If you need to write out gamma instead of it looks like an upside down fish symbol, that is the symbol for gamma, so gamma rays. Then we have X-rays. I'm sure you're familiar with those. Next to X-rays is ultraviolet. I'm going to abbreviate it UV. I know you've heard of that too. Ultraviolet. And if you can't remember the abbreviations, write them down. This little piece of the pie that I have kind of broken out to, this is going to be our visible spectrum that we're going to look at. These are all the colors that you see. And then right next to the other side of the visible spectrum is infrared. I'm going to write it as IR, infrared. And then we're going to look at microwaves and radio waves. And we can break down these into other sections like short wave, long wave, radio waves, TV, FM, AM, radar. But those are the main 7 that we're going to look at. So 1, 2, 3, 4, 5, 6, 7. Those are the 7 types of electromagnetic radiation, and you need to know them in order. And by in order, I am talking about what has the highest wavelength, the lowest, what has the highest frequency, the lowest. So going back and looking at those numbers, you don't have to memorize the 10 to the negative 2, 10 to the 19th, those numbers for wavelength and frequency, but you do need to know which side has the smallest values and which has the largest values. So I'm going to present a few questions, see if you can pause and answer it before I give you the answer. If I asked you between gamma rays, X-rays, and UV, which one has the highest frequency, your answer is gamma rays. If I asked you between IR, infrared, microwaves, and radio waves, which has the shortest wavelength, your answer is infrared. And if I were to ask you between ultraviolet, visible, and infrared, which has the smallest frequency? Between ultraviolet, visible, and infrared, which has the smallest frequency, your answer is infrared. So those are the types of questions you should be able to answer, but there is some memorization and in the proper order that you need to go through. Now we're going to break out our visible light. The visible spectrum, if you think of the colors of the rainbow, we've got first up, we've got our red. And next to red is going to be orange and yellow. Then we have our green, our blue, indigo is going to be next, and then violet is going to be on the far end. So looking at that, we've got red, orange, yellow, green, blue, indigo, and violet. Now, the way all of this is drawn originally, those letters are back. But if you have ever heard of Roy G. Biv, that's the color of the rainbow. That is the visible light spectrum that we can see. And you need to know the visible light spectrum in order. So again, I'm going to ask you some questions. Within the visible light spectrum, which color has the highest frequency? Your answer is violet. Within the color spectrum, which color has the longest wavelength? Your answer is red. Your answer is red. And I could point out, okay, what about the three here in the middle? Yellow, green, and blue. Of those three colors, which has the highest wavelength? The highest wavelength. Your answer is yellow. So please look this over. Make sure you get that information down. Now we're going to add energy to this transition. So we've got wavelength, we have frequency, and energy and frequency. Energy, we're going to use a capital E, and then our frequency is right there, talking about relationships. Energy is directly related to frequency. Energy is directly related or directly proportional to frequency. What that means is energy and frequency either increase together or they decrease together, but they transition numerically in the same direction. So directly proportional are energy and frequency. You've already noticed from the numbers that frequency and wavelength move in the opposite directions. So we say they are inversely proportional to each other. Inversely proportional, meaning as one of those variables increases, the other one decreases, and that can go either way. So if I throw energy in here on my spectrum, since frequency has a really high number down here, expect high energy on this end. Since energy and frequency are directly related. And expect on the opposite end where frequency is low, you're going to have low energy on the opposite end. Something that you can relate to, gamma rays. What gives off gamma rays? Hopefully the sun come to mind. The sun has a ton of energy. Y'all are aware of that. X-rays, they make you wear the lead vest whenever you are getting X-rays, depending on what part you're getting X-rayed, because there's so much energy wrapped up into X-rays. Ultraviolet also comes from the sun. You wear sunblock to block out UVA, UVB rays, and those are on the left side of this where your frequency is high, meaning you also have high energy. So if I were to ask you within the visible spectrum, which of those colors has the lowest energy, your answer should be red. So we have energy and frequency are directly related. Frequency and wavelength are inversely related. Now we can add on energy as it relates to wavelength. Energy as it relates to wavelength. How are they related? Hopefully you see that the higher the wavelength, the lower the energy. So energy and wavelength are also inversely related. So we had lots of information going on within that drawing. Make sure you got all of it detailed within your notes. Moving on, we are going to throw in a couple of equations within this section, but we are not going to do any calculations directly within the section. If we get to go back and do our lab, then we will throw in the calculations once we introduce the lab. So frequency and wavelength, they are mathematically related to each other. There's your lambda and nu symbols. The C itself, the C stands for the speed of light, and its units are meters per second. Wavelength, again, is the length of a wave, typically in meters. Frequency is measured in hertz. They have thrown up a different unit right here. So S to the -1, that's like writing 1/seconds as the unit, which is the same as the hertz. So 1/second is the same as the hertz. The speed of light, as we look at it, just so that you know, the speed of light is a constant value, and it's going to be really close to 3 × 10⁸ meters per second. So when you multiply wavelength and frequency, numerically you will continue to get a constant value close to 3 times 10 to the 8th meters per second. This is just another illustration. This is looking at actual waves on a beach instead of light waves. The top one, the wave coming in, you can see it has a very long wavelength as compared to the really short wavelength below. But if I were to ask you which had more energy related to it, well, we stated earlier that energy and wavelength are inversely related. So with the tiny wavelength at the bottom, it's going to pack a lot of energy. Moving on to the photoelectric effect. Photoelectric effect. Its definition is referring to the emission of electrons from a metal when light shines on the metal. So when light comes in, shines on a piece of metal, electrons are knocked loose. That's where the word emission comes from. And the particle description of light. So this whole section up till this point, we have talked about light acting as a wave. Now we're going to look at light acting as a particle. And the word quantum is a minimum amount of energy that can be lost or gained by an atom. So the word quantum refers to a minimum amount of energy lost or gained by an atom. And we're going to go look at the experiment setup to show the photoelectric effect. This is it in a nutshell. I am going to go redraw it. So we have an enclosed glass tube, and within that enclosed glass tube, you've got 2 pieces of metal. One is going to be a collecting rod. So in the gray is our collecting rod, and in the other is going to be a larger piece of metal that we're going to shine the light on. So this is a larger piece of metal here that we're shining the light on. Now, notice those 2 pieces of metal are not actually touching each other, but we are going to have electrical lines that come out from the bottom touching this one. And we're going to go over here, we're going to draw us a little sensor. It has a dial on it that's on 0, and we'll see if it changes. And then this is going to go over to some type of electrical outlet source. And again, that is connected right there. So you should know that the flow of electrons needs a full path so that it can continue to flow. And we are gapped right there. So a big gap in that particular position. And in this experiment, we've got light that is coming in and hitting this piece of metal. So light's coming in, hitting that piece of metal, and what happens is electrons are knocked loose. You can't see the electrons knocked loose, but they are knocked loose, and they come over and they are collecting on the collecting rod. That basically completes our circuit, so the electrons are flowing, and then all of a sudden this needle that's on 0, you get a reading on your scale that says, hey, I have a completed electrical path. So something has to be going on within that light to complete that electrical path. So if we go back to the photoelectric effect, and that is what we have here that we're showing. Hopefully you're getting your labels on everything. That is the emission of electrons from metal when light shines on the metal. So the electrons are knocked loose. We have a completed electrical path. So within the light, you do have electrons that are being knocked loose. But that means within your light, something has to be in the light to knock your electrons loose. Well, light's not considered matter. Light does not have mass. But what light does have is a photon, and we'll give you the definition of a photon. It is a particle of electromagnetic radiation that has zero mass, but it carries a quantum of energy. No mass, but it does have a tiny amount of energy that is associated with it within the light. And that energy is enough to knock electrons loose. So it is knocking the electrons loose. A great example of where the photoelectric effect is used is going to be solar panels. Solar panels. So here we have our second equation that we're going to look at. E stands for energy, H times V. For now, it's just more important that you know what each of the symbols represents. There's nu again, which is frequency. H is a new one, though. That is Planck's constant. You do not need to memorize the value for Planck's constant, but you do need to get this down and know what each variable stands for. And if I were to rearrange this, kind of like the other one, and you've got the constant, Planck's constant by itself, it would be energy over frequency. And since we are dividing the two variables to get a constant, they are directly related. So the word divide and the word direct both start with the letter D. Dividing two variables to get a constant, that constant is H, they become directly related. So energy and frequency are directly related, as we discussed earlier. So there's your photon again, its definition. I stated it earlier. It's a particle within your electromagnetic radiation, or your light, having zero mass and carrying a quantum of energy. And they're just saying the same equation we just looked at also holds for the energy of a photon. I will highlight important parts of this video once it's completed.
In 1900, Max Planck theorized that a hot object does not emit electromagnetic energy continuously. Instead, Planck suggested that objects actually emit energy in small, specific amounts, or quanta. Energy, he said, was quantized. In other words, the energy being emitted has only certain values, almost as though the energy is a packet. Some wavelengths of light carry only a little energy at a time. Others carry more. But the energy is always quantized. It is always in terms of the packet. The smallest possible amount, one packet or quantum, is defined as the minimum quantity of energy that can be gained or lost by an atom. Quantization becomes important when light or another form of energy interacts with an atom. Sometimes the incoming energy is enough to make something happen, other times it is not. Think of rolling a ball out of a pit. The energy must be enough to get the ball out of the pit all at once, or the ball will simply roll back to the bottom. Even if the energy of multiple rolls would add up to enough energy, the ball will not have been able to get out of the pit because the energy of each hit in itself was not sufficient. With enough energy in a single hit, the ball escapes from the pit. Similarly, if the packet of energy is not large enough, the atom is unaffected, despite the fact that the packets of energy keep coming. If the packet of energy is sufficiently large, however, the atom is affected. An electron, for instance, may become excited.
So we will talk about those excited electrons momentarily. Make sure that you get the definitions that are right over here for quantized and quantum if you don't already have those. And they were mentioning these packets over and over, trying to get you to think about the energy that is coming out. So the packets of energy emitted from light. And it is a specific amount that we are talking about. So just because you throw energy at it, if it is not in the right amount, your electrons might not be affected. And we will look at these electrons that are moving, becoming excited, as she had stated. So here we have ground state. It is the lowest energy state of an atom. So if your atom has multiple electrons or even one electron, those electrons want to live as close to the nucleus as they can to be in their ground state. But if an electron gets excited, it's going to move to a state of higher potential energy than what it was in ground state. And just a couple quick, and we're going to look at another video. So if we have our nucleus right here and we have our electron clouds right in here, just making very simple models. If you have an electron on that first energy level, and again, that first energy level is what's going to be closest to the nucleus, then that electron can gain energy to jump out or excite itself and transfer to a higher energy level. So if it does that, it can jump out to a higher energy level. Before we watch our video, I'm going to do just a quick drawing because we're going to look at Bohr's model of the atom and talk about hydrogen's line-emission spectrum. Again, you have your nucleus here. We've got rings, or according to him, what he thought were orbits, where electrons could go around the nucleus, kind of like planets do. You can have closest to the nucleus, that's where electrons want to live in their ground state. But if you have multiple ones, two can live on the first, and then let's say we fill this one up with electrons, and then we continue to move on out. These electrons are technically in their ground state, but they can jump energy levels. This one, if it gets just the right amount of energy, it can jump 1, 2, maybe 3 or more energy levels. The other ones, just depending on how much energy they have, maybe this one gets energy just to jump 1 energy level. But they are going to get that energy, if we're talking about electromagnetic radiation now, from those little packets where the photons are at within the light. The electrons are going to temporarily absorb that energy, jump to a higher energy level, and then they're going to kick this photon out, drop to a lower energy level. Take great notes and get your drawings, because there's going to be multiple things to draw within this video.
In the late 19th century, scientists observed that a characteristic lavender light was produced when a high-voltage electric current was passed through hydrogen gas. When the lavender light was sent through a narrow slit, then through a prism, it separated into distinct lines of different colors. In 1913, the Danish physicist Niels Bohr proposed a model of the hydrogen atom that explained atomic spectra. The Bohr model introduced the idea of quantized energy states for electrons in atoms. In the Bohr model, the electron moves in circular orbits about the nucleus. According to the model, the electron can circle the nucleus only in allowed paths or orbits. When the electron is in one of these orbits, the atom has a definite fixed energy. While in an orbit, the electron can move to a higher energy orbit by gaining an amount of energy equal to the difference in energy between the orbits. When a hydrogen atom is in an excited state, its electron is in a higher energy orbit. When the atom falls back from the excited state, the electron drops down to a lower energy orbit, and a photon is emitted. The emitted photon has an energy equal to the energy difference between the higher energy orbit and the lower energy orbit.
Okay, so you did see hydrogen's line-emission spectrum, and then it's showing you about electrons that get excited or de-excited, going back down to ground state, and looking at the Bohr model of the atom. This is going to be our fourth model of the atom that we are looking at. So I'm just backing up again to the picture for hydrogen. So we're specifically looking at hydrogen. It's got 1 proton, 1 electron. Hydrogen gas is going to be colorless, but you can see they have electrified it. They're running a current through it there on the left, and it's got this pinkish lavender glow to it. They want this light to be a narrow beam before it goes into the prism. And prisms, they have gradients to break apart what you see. You know, just from working with different inks, if you mix yellow and blue together, you get green. If you mix red and blue together, you get purple. Light works in a very similar way. Just because you see a pinkish color, if you were to break it out, in this case, for hydrogen, that pink color that you see, you have 4 distinct wavelengths of visible light that are blended together to give you that other color. That 5th line that you are looking at is just in the ultraviolet region, so not necessarily that we can see that, but it does play a small part in the overall color that we see. And you want to make sure that you have the definition for orbit. It's where the electrons circle the nucleus in allowed paths. So according to Bohr's model, electrons can only live within these allowed paths that circle around the nucleus. Within that last video, they also talked about the words emission and absorption. Get those definitions. Let's start with absorption first, because that's what's going to happen is energy that is part of that photon. Energy is going to be absorbed or added into the atom. It's going to move that electron from a lower energy level to a higher energy level. That's called absorption. It will only stay there for a fraction of a second, and then that electron kicks the photon out. When the photon is emitted, the electron is going to fall to a lower energy level, and that is called emission. Here's a graphical representation of that. Again, on the left, that orange wavelength of light you see, it is coming in, and that electron is going to absorb the energy from the light. And then the green wavelength that you see exiting on the right side, that is the photon getting kicked back out from the electron. And at that point during emission, that is when we see the light. So we don't actually see the visible light during the absorption part of this. We see the light during the emission part of this process. Please get these models drawn that you have. Again, the first model we've talked about is Dalton. Dalton thought everything, the smallest you could get was just the atom. So we think of a sphere as being our atoms. And then next is Thomson.
Thomson discovered the electron and proposed the plum pudding model, where electrons are spread on the surface of a solid, positively charged sphere. The discovery of the electron showed that the atom is, in fact, divisible.
So that's our second model. The third one is Rutherford.
Rutherford learned that atoms are mostly empty space with negative electrons scattered around a positive center. This model describes a central part in the atom, the nucleus.
So we've gone from discovering the electrons with Thomson to discovering the nucleus with Rutherford, and then we move into our Bohr model that we talked about today.
Bohr's model suggested that electrons move in orbits around the nucleus. Bohr was the first person to be able to explain why atoms could only give off or absorb energy in specific amounts.
And by the time this chapter is over, we will talk about our fifth and final model, which is the current modern model of the atom, the quantum model.
We now know that electrons are not solid particles that can orbit the nucleus like tiny planets around a sun. In the present model, electrons are found in regions of probability that are often shown as clouds that surround the nucleus at successively higher energy levels.
So again, that present model they're talking about, you can go ahead and label this one the quantum model. We will get into more specifics within this chapter.